this work, even though I'm the one presenting it, wouldn't have been possible without many, many collaborators over multiple years at this point. To start off with, I'd like to mention Mario Burgess from the Civil Engineering Department. He's been a very close collaborator that's been working on some of the non-intrusive load monitoring aspects of the work and really bringing in a flavor for some of the building aspects of it. Also pointing out Gaurav Bhatia, some of the ECE folks, Jose Mora, Raj Kumar, and Bruce Krogh, who have been, again, working on many of the different layers of the system we're going to be presenting. And most importantly, I'd like to point out the students who do most of the real work behind the system. Okay, so to get started, I'd like to motivate the talk by looking at where energy usage typically goes in the US right now. So if you look at this pie chart, we see at a high level that industrial takes about 27% of the energy, and they've been sort of conscious about energy for quite some time, so there's been a lot of work on optimizing that already. If you look at transportation, it takes up another 34%. And transportation, of course, is a hot topic, and people are talking about hybrid cars and different sort of public infrastructures. So again, it's a relatively high barrier to entry. But if you look, the biggest slice of energy usage in the US, 39%, is consumed by buildings. And buildings, as it turns out, even though it's the largest slice, tends to harbor a lot of relatively low-hanging fruit when it comes to what we can do from an efficiency standpoint. So what I'd like to do today is talk a little bit about how sensor networks can help improve energy efficiency of buildings. So what type of things can we do with sensor networking technology? So the first is that we can accurately account for energy costs and load distribution. So imagine having sensors all over the environment so that you can figure out where your energy is going, what different devices are using it. Next, we can look for anomalies in the system, right? We can look at patterns over time, and we can see if some particular aspect of a building is misbehaving or performing very abnormally compared to what it would normally do. And that would sort of flag a facilities maintenance person to come and perhaps inspect or replace equipment. You could imagine in a system where you have control as well, so you have both sensing and control over the infrastructure, we could start to do things like shut off unused loads inside the system to help automate energy management. And then finally, and some of the stuff that I'm going to be talking about towards the later half of the talk, is we can start to correlate environmental data, occupancy data, time of day usage, energy usage, heat profiles of buildings to essentially do sort of a next layer of optimization across how the system sort of consumes energy on a day-to-day basis. And finally, we can start to monitor appliance performance. And this goes back to sort of maintenance and anomaly detection. But it turns out in a lot of buildings over time, big consumers like chillers tend to misbehave and sort of deteriorate over time. So we can actually try to identify and target these as places to optimize. So the sort of grand challenge here is eventually to hopefully support zero net energy buildings. So buildings that over an entire climate cycle could actually collect energy from sources like solar or wind power and be efficient when those aren't available to have a zero budget total. So for most of this talk, I'm going to be focusing on how to accurately account for energy sources. So if we look at building electrical usage, you typically see that some percentage goes towards refrigeration, some percentage goes towards air conditioning, water heating, space heating, and then we have this big chunk here that basically is consumed by lighting and other miscellaneous devices. So as it turns out, that big 52% chunk is something that we really have very little information about, right? So if you think about how you buy electricity right now, you basically get some sort of bill that looks like this, maybe from Duquesne or whoever your electrical provider is. And if you're lucky, you essentially get usage of energy by the months. And some providers will even provide you the weather information to correlate with this. But that doesn't really tell you all that much about where your energy is going, right? What you really want is something like a grocery list, right? You want the shopping list for your energy where it says, okay, I know exactly which devices in the system are consuming what. So the first question we have is, how would you go about designing a system that's low cost, effective, easy to deploy, that could potentially give you this type of information, more the shopping list of where your energy is going, as compared to just giving you your overall monthly bill that you have no way of really verifying. Well, if you look at electric metering coverage, the first thing that we'd want to do is basically just have appliances report how much energy they consume. And this is something that people have been talking about, but really up to this point, there's been very little traction in having appliances really internally compute their usage. So the next best thing is probably to do something like plug level metering, right? So you can imagine putting a meter at each different appliance device. You could locally collect the information, but this would cost, and this is sort of a ballpark number depending on volume and scale, all those good things. But you could imagine $50 to $100 per appliance, which given the cost of electricity now is pretty steep for getting a payoff. The next thing you could look at is, say, circuit level energy consumption. So if you go out to the circuit level, you might have a meter that costs $100 that gives you information about an entire circuit. But here, you're already starting to see that decline of, yeah, you're paying less, but now you have a bunch of different devices that are potentially operating on each circuit, right? So you don't have quite as fine granular information as you would with something like plug meters. And then finally, you can imagine just having the mains meter report data, and that sort of essentially gets you back to the state where you're getting your bill from something like Duquesne. And the other thing to remember here with adding these types of electric metering devices is that Moore's law doesn't apply to labor, right? So even if you did want to go ahead and install plug level meters in all of your appliances, so we've actually done this in our group multiple times to get ground truth data for some of the stuff that we're going to be talking about next, it's very time consuming, very tedious, and would typically be out of the reach for most sort of commercial type installations. But let's say you're looking at something like mains level metering. So one thing you could do is look at, for example, electric usage on a day-to-day basis rather than your monthly basis, which is what you're getting from the utility companies already. And here, we can kind of see trends. So this graph is showing energy consumption of an apartment in Shadyside as compared to temperature. And you see some sort of rough correlation that when the temperature gets low, the energy consumption gets higher, probably because they have electric heating. But beyond that, it's very hard to sort of see what's happening in the system. Imagine you looked at the energy with one sample per minute instead of one sample per day. Well, now you can actually start to see some characteristic patterns in that data, right? We can see something like perhaps a compressor that's running periodically. You start to get some idea of what else might be happening inside the system. If you go one step higher in resolution, so this example is showing, of course, a coffee machine. So it's one of those fancy coffee machines that can produce a bunch of different types of drinks at 1 hertz resolution. Now we start to see a lot of information about what's happening. We can see the water boiler periodically running. We can see at this point somebody asking for a cup of tea. So that sort of characteristic waveform looks the same across 2 different points. You can see at this point somebody asking for a cup of espresso, and then here asking for a cappuccino. So you basically start to see that as we sample at higher and higher speeds, you get more information from the waveform about what's actually happening behind the scenes. So this approach is called non-intrusive load monitoring. So the idea being that you connect a high-fidelity energy meter at the mains that's sampling at a very high frequency, and it's essentially doing pattern matching on these signals to try to disaggregate what type of devices are running in the system. And there's sort of 2 different general approaches to this problem. The first is looking at steady state changes in energy consumption. So you can imagine if your power goes up by 60 watts, you could maybe infer that a 60-watt light bulb is turned on. The other thing you can look at, which is potentially more interesting, is the actual shape of the transient. So what does that particular curve look like? And based on that curve, perhaps you can start to do some classification of the different types of devices. So if you look at sort of the challenges here, the first is detecting when these events occur. So this shows an example from, again, a house in the Pittsburgh area where, depending on what type of appliances are turning on or off, different energy levels change. And so you can sort of see where you'd want to take a snapshot of high fidelity information to try to classify. The next challenge, once you've sort of identified these regions where events are activating, is classifying the event. So this picture shows an example of a transient in both real and reactive power space of a refrigerator turning on and off. And what you can see here is that basically it's a sort of very different looking waveform for each of these different states. And so the idea being that if you had a clean version of this, you could do any number of different pattern matching approaches to try to identify what type of appliance was actually running. So if you look at sort of your typical installation for this type of system, you would take some sort of energy metering device. So this is a picture of a wireless panel meter that we've developed, which you would connect to the mains of your house, your apartment, or your building that you're trying to monitor. And then essentially everything that's connected to it would be piped through that system. So sort of in the ideal world, this would be something that's relatively easy to connect. In a real deployment, things are, of course, never quite so clean. So this is a picture of the board connected to an energy panel meter that didn't really have enough room inside it to put it in. So we had this temporarily running with debugging cables connected to it. So it seems like this approach, assuming it would work, would be sort of solving the problem, right? We said $100 to cover your entire house. Well, unfortunately, there's a bunch of limitations with these types of approaches. So the first is training. You have to label all of these different transients, and you have to match them to different appliances. And so the sort of first question that comes into our mind is, well, how well do these transients generalize? So if I train a refrigerator in my house, will that refrigerator be have the same type of pattern as the one in CIC? And as it turns out, the answer is yes and no. So there's a lot about the actual sort of network of the electrical system that changes it, and also these appliances change based on brand, type, how long they've been running. So you get some level of generalization, but certainly not enough to actually go into a new environment and be able to classify all of the devices. The next issue has to do with temporally close transients. So imagine you have two waveforms like this. So this is potentially a refrigerator turning on, and then some time later something else turning off. We can grab this transient. It's very clean. We can classify it. Grab this transient and classify it. What happens if the two are very, very close to each other? Instead, your event detector would grab this type of signal and now be essentially confused about which device actually turned on or off. This could be some third appliance that looks similar. And the final problem here is essentially continuously variable loads or appliances with hidden states. So if you imagine something like a more sophisticated heating and cooling system, we have fans that slowly ramp up and ramp down their energy usage over time. So that's what we call continuously variable loads. They don't have these sharp transients that are easy to pull out. They essentially just shift the whole power usage slowly over time. The other thing is devices with hidden states. So if you look at something like a washing machine, it actually goes through a whole bunch of different cycles and transients, different sort of modes of operation that would all look like individual distinct appliances. So the idea behind some of our work with sensor networks is, what can we do to try to simplify the deployment problems here and try to increase sensing accuracy? So we advocate essentially using this meter level data, doing our non-intrusive load monitoring approach, but then integrating that with low-cost endpoint sensing. So the idea would be to have different sensing devices that are physically distributed into the environments that allow you to try to reinforce that training process that happens. So if you look at the sort of approach with NILM and low-cost sensors, the sensor data is physically independent, right? So you don't have nearly this issue with temporal closeness that you had before. If, for example, you have a light sensor in one room and you see a transient, you see power usage because lights turned on in that room and lights turned on in another room, you can actually very easily differentiate those two sources. Of course, the downside is that sensor data in real environments tends to be extremely noisy, and oftentimes it's hard to tell if it was really a light turning on or if perhaps somebody raised a window shade and sunlight came down on it. So you essentially have to have this back and forth approach where the two systems can reinforce each other. So I want to talk a little bit about the wireless sensor networking technology that we use in this project to essentially capture this type of data. So to start off with, I'd like to highlight sort of the FireFly wireless sensor networking platform. And I brought some of the hardware with me today that you can pass around. So these are the devices that are used in the system. And essentially, we start off with our core platform. So the upper left image, it's basically a microcontroller with a low-power wireless radio built into it. And so the idea is that this can process sensor data. The picture to the right shows you an example of the board with the sensors attached to it. And I have one of those that's in the box that is being passed around. And the idea is that this can sense temperature, acceleration, vibration. So if you connected this to something like a heating or cooling vent, it could detect if it was vibrating because the vent was turning on. Air pressure, which is very good for monitoring, again, heating and cooling changes in a building if you have air compressors that are pushing air down into it. An audio sensor and a PIR motion detector, so those are good for determining occupancy in rooms. Of course, a light sensor and humidity. So basically all of the different environmental parameters that are related to comfort and occupancy in rooms. We also have a plug meter device, and I have two versions there, one that's open and one that's closed. You can see the guts of what's inside of it. But this is basically something that allows you to sense the energy consumed by an appliance and then also remotely turn the appliance on and off. And again, it has the same radio technology that the sensor platform is using, so it can relay this information wirelessly. And then finally, we have an electric panel meter, which unfortunately ours are all being used right now, so I didn't bring one along with me. But this allows you to connect to the mains and do that high frequency sampling that you need in order to grab the transients to do the NILM classification. I also want to talk a little bit about some of our very, very new sensing technology. So we're also developing a low power thermal scanner. So the idea is to use something like the thermal guns that you point at engine blocks or cooking pads to determine temperature. We have a low-cost version of that which can scan on a pan tilt head and actually build three-dimensional models of the thermal mass of the building, which can be very useful for doing things like HVAC tuning, occupancy detection, and looking at how materials expand and contract with thermal properties over time. So if you take all of these components together, we have a bunch of different mesh networking protocols and a bunch of system and operating system support to essentially efficiently relay and collect this information. So in a typical deployment where we're monitoring a building, we'd have a bunch of these leaf node devices. So we'd put the sensors out throughout the environment, and these could communicate over multiple hops back to either a wireless gateway or a wired gateway. And so in these examples, and in most of our deployments, we typically use an OpenWRT-based Linux router that we've essentially reflashed with our own version of Linux, our own software to collect this information. And then we have a system infrastructure support, which I'll talk about later, called Sensor Andrew, which we use to push that information back to a central server and any different agents that are interested in processing it. So in this particular application, I want to talk a little bit about a unique sensor which we developed for doing this non-intrusive load monitoring disaggregation. So here's a picture of what we call the FireFly EMF detector for electromagnetic field. And this is a device which actually senses changes in both magnetic field and electric field. And I'll talk about sort of the distinction there. But the idea is that you can put this near an electrical appliance, and then it will detect changes in the current draw of the device from a distance. So the idea being, in a lot of cases, you have things like overhead lights, you have fans, you have embedded wiring and electronics, which are hard to put plug meters on. So we developed this device which can essentially be put near the wire. So you could stick this as, say, a patch next to an electrical outlet to detect when that outlet is turning on and off. And so I don't want to go into the details of the circuit, behind it, but basically the magnetic field detects current flowing. The electric field, so electric field is generated by a change in voltage, so that detects the presence of voltage. And through a simple example, you can see why that, what that distinction is and why that might be useful. So here, I have an example where we have a light switch that's controlling an overhead fan, and the overhead fan has a cord to turn it on and off. So at point A, we see that when you flip the switch, you actually connect the circuit so that there's a voltage potential, right? In this case, the fan is not running yet. There's just voltage going to the fan. And what you see here is that the electric field detector starts detecting that there's a voltage present. At time B, we actually pull the cord on the fan, and what you see there is, so the magnetic field is shown here, and this is showing you the energy envelope of it, so basically the amount of energy detected in that signal, which is what we use to process, and you actually see that when current starts flowing, the magnetic field spikes. And so what we can do is we can essentially use the combination of electric and magnetic field to significantly refine and reduce sources of noise in the system. We can actually tell if the device is placed closely enough to a wire, or if it's just sort of a spurious transmission we're detecting because somebody's cell phone walked by near the device. This is just sort of another example. Some interesting things we're thinking about now is actually looking at the signature of these magnetic fields. So here's an example of what it looks like against the side of a computer when the computer is booting up, doing some processing, and then eventually going back to sleep to turn off. So in our system framework, essentially, we can put these electromagnetic field detectors out in the environment. We can put plug load meters in places where it's possible. And the other thing about the plug load meters is you have the ability to actuate the device, right? So if you ever want to actually turn something on or off so that you can remotely control and save energy, you really do need something in line that has actuation capabilities. But so if you look at sort of this simple example, the three-phase meter is going to give you energy over time that looks like that. You can then essentially take the data from the magnetic field detectors and from the other devices to sort of backwards figure out which devices are on and which are off in those cases where you might have confusing signals. And in this case, the EMF detector is only going to detect a change. It's not going to actually label the change. It's not going to tell you how much energy it consumed, but you can get that information if these devices are time synchronized back to the main energy meter. So if we go back and we look at essentially the NILM limitations revisited, the first one was the training process, right? So now we actually have the ability to throw these sensors all over the place and essentially use an unsupervised training approach. So as long as we have some sort of tag that identifies what they are, we can slowly learn over time what transients are related with which tag. And the idea is to let this run for a couple weeks at a time, so you actually get many, many, many more transients than you would have by sort of a manual training phase. You could also imagine leaving some of these devices in place over time and using it to do continuous training. So as appliances change, you could actually capture those changes in the transients. What about temporally close events? Well, clearly now, since we have individual sensors near them, or at least groups of sensors that can help refine that, you can sort of eliminate those, or at least discard cases where two appliances turn on next to each other that could be confusing for the NILM system. So what about continuously variable loads? Well, we can add plug meters to capture some of those. That approach works. And we've also been thinking about using the intensity of the electromagnetic field detectors to try to help in that. But still, that's essentially somewhat of an open problem. And again, devices with many, many internal states is still something that's challenging for us to deal with. We have a couple approaches which we're experimenting with. So once you have a system like this, the first sort of obvious question is, what can we do with all of the data? So we've had all of these deployments where we've essentially stuck in tens. In fact, in my house right now, we have a system set up where we have around 56 different plug meters and sensor devices collecting data. So the question is, what can we do with that data? Well, we can start to do things like appliance usage classification, occupancy-based waste detection, anomaly detection, and I'd like to sort of visit and talk about some of those next steps. So one thing that we do with the environmental sensors linked with the electrical sensors is we can actually try to classify appliances based on how people interact with them. So the first thing that we can look for is things which we call background appliances. These are things that are essentially always on, they're always consuming energy, and they're essentially detached from people's interactions. So if you looked at having a motion detector, for example, in a kitchen, most of the time the motion detector turning on and off isn't going to be heavily correlated with how the refrigerator is running. In this example, it turns out a refrigerator is slightly correlated, but if you imagine something like just a phantom load in your house, you'd basically see no correlation at all. So in those cases, if we can identify that that load is a background load, we know that essentially all we can do is look for anomalous detection. There's really no control that we can do with a device like that. The next class of devices we'd look at are, say, we call passive devices. So these are types of appliances where the user interacts with them at first and then essentially lets them run on their own without interaction. So the sort of classical example here is the washer and dryer. A motion detector that's in your laundry room would detect activity when you're starting to use the washer and dryer, maybe periodic activity, but generally speaking, the device essentially starts and runs for some fixed duration and shuts off. So the thing that we can do here, again, of course, we can do anomaly detection and talk about maintenance, but we can also classify this as a potential load for peak shifting. So imagine your utility company, they're trying to reduce their peak power load so that they can cut back on how many different generation plants they need to build. Peak load for them is extremely important, and they'd love to know in neighborhoods or in commercial environments how much of this load is actually shiftable. People have talked about load shifting, but it would be great to have some real numbers that defined what the potential was there. And then the last category of appliances that we'd be able to detect are active ones. So these are things like TVs, overhead lights, where you have a very strong correlation between occupancy, motion detectors, audio sensors, and the usage of the appliance. And these are sort of the fun examples, because here we can start to do things like automatically shut loads off, right? So if we see examples where overhead lights are potentially on, when nobody's there, we can suggest to the user, hey, you leave this light on 45% of the time when nobody's there. This is using up X amount of your energy. Why don't you either allow the system to automatically shut it off, or at least be more aware of that? So there we can start to think about doing occupancy-based control. So the other interesting thing that we see when we start to do this correlation between sensor values and the actual appliances are clusters of different devices. So this is a feed that was, this is a graph that essentially shows different sensors, both environmental and power sensors, and the distance between the sensors that are connected is related to how tightly they were correlated over a 1-week period. And so what you start to see is different sort of usage and location clusters within building environments. So for example, in the kitchen, if there's a sound system in the kitchen, it tends to be correlated with the kitchen motion detector and the kitchen overhead light. And again, this is what we can sort of pull in to do that classification, where we're trying to figure out what types of appliances are responsible for what inside the system. This was all done in a completely unsupervised fashion, right? So we didn't actually label where the devices were. The system can learn that over time by just looking at correlation. So the next step is, once you have these clusters built and you've classified things, for example, as an active appliance, you can now flag areas where there is potential waste. So in this example, I show a trace from the living room from my house. So the cluster, of course, was automatically generated by doing the correlation. And then the system essentially learned that most of the time, the motion is correlated with my living room light and my sound system. But then it'll flag particular areas like this, that green blob there, where there was motion, energy started being used, but then the motion stopped, right? So it can internally keep track of that and start to provide that feedback to users to suggest areas of waste. And again, all of this can happen in a very unsupervised fashion, so it's very sort of intrusive to the user. And then, of course, we can start to look at anomaly detection. So here you see an example of energy from a refrigerator over time, and here we show sort of an automated threshold detector, which we run on top of the system, and essentially see that, yeah, there's some spikes in usage, but generally it stays relatively consistent over time. If you look at something like usage from a television, you actually see something slightly different. So there are certain days, in this case, I think that spike was when Wimbledon was on, and the TV is basically sitting on all day. You actually see that spike, and that would get flagged as sort of anomalous behavior. So the system could mark and say, hey, you know, is something really wrong here, or is this something that you're sort of aware of? So we'd like to see that type of labeling come into a user interface to help guide facility managers or homeowners to sort of monitor their usage. And sort of the last step that you can imagine is taking this to the global level. So thinking outside of just one building, outside of one just home. I talked a little bit about how information about peak shifting could be pushed up, but imagine at each different sort of layer within the smart grid itself, percolating this information up, using it together to build a sort of more precise model of how energy can be used, how energy can be shifted around, such that people working on transmission and renewable resources have the type of numbers which they need to essentially optimize their systems. So in order to support this type of scenario, and I talked early on about a little bit about how we had a backbone to collect information, I'd like to sort of talk a little bit about internet scale sensing and the Sensor Andrew project. And for this, hopefully I can actually give you guys a demonstration of Sensor Andrew. But the idea here is that more and more information, more and more physical information is becoming sort of available in the cyber world. And the question that we need to ask is, how can we utilize this information? How can we share it? And how can we actually put it into a form that's consumable by developers so that they're not sort of reinventing the wheel every time they try to interface with one of these types of devices. And I like to show this slide as sort of a motivation for that. So this is a picture from the top of Margaret Morrison on top of the Intelligent Workplace on campus. So they do work with intelligent building spaces that are supposed to sort of react to the environment, to be energy efficient and friendly. And what you see is two weather stations that are essentially almost identical next to each other. And what happened here was, one project came along. They decided they needed weather information. They needed to know what direction the wind was coming. So they put up a weather station. They built a nice interface for it. They had a digital feed, which they used for their project. Somebody hopefully wrote a very nice PhD thesis on some system they were building around that. And then a couple of years later, somebody decides, oh, I also need a weather station. But didn't even realize that that one had existed. The student had left and gone. There was no sort of access to that information anymore. So what do? They go up and put an identical one next to it. So it's not just students building projects that suffers from this problem. If you look inside buildings, you see tons and tons of redundant sensors that are part of different infrastructure subsystems. So ideally, we want to come up with a way of A, searching for these. So how do you know that there's this sensor available? And then B, how do you actually make it accessible to users? And that's sort of the idea behind the Sensor Andrew project. So we want to create this infrastructure that helps connect the virtual world to the physical world. We have a whole bunch of different challenges associated with access control, storage, describing the physical sensor information, and then at the same time, we want to help maintain security and privacy, right? You don't want to have people be able to connect to your house, turn your lights on and off arbitrarily. You potentially don't want to leak that information to other people. And then we also need to deal with performance aspects of, how do you deal with tens of thousands of these data feeds in an extensible manner so that you can collect it and process it at the back end. So a little bit about why we call it Sensor Andrew. So the idea of being at CMU, we started off with Wireless Andrew, so named after Andrew Carnegie, Andrew Mellon. We moved on to Wireless Andrew. So the hope is that Sensor Andrew will be sort of the next evolutionary step from that, where we make CMU one of the most sensed campuses on the planet and really have a workable infrastructure where people can develop applications on top of that. So a little bit about the backbone of how it works. We've developed what we call Sensor over XMPP, or SOX, and this is essentially an XML-based message passing system. So for those of you that aren't familiar with XMPP, it's the backend which they use in Google Talk, and actually it's also now what they use as part of Android at Home. So being able to have the different devices in your Android at Home environment send messages to each other. So what we added to that was essentially our SOX schema, and we have a XEP, which is essentially a description of the protocol, which is going through a process to be approved as part of the XMPP standard right now. And we've, of course, also built a SDK on top of that, so allowing developers who are familiar with C, C++, Java, Python, I think we probably have a couple more languages supported now, but an SDK that allows them to quickly develop applications which can get access to these different data feeds. And then finally, as sort of part of our schema, we've had to come up with our version of a sort of standardized way to describe transducer data. We needed to deal with things like units, location, what the values should be, how to deal with sort of handoffs between devices. And this turned out to be one of the more challenging aspects of the project. If any of you are familiar with platforms like PatchBay and other like SensorMap from the Atom project from Microsoft, a lot of problems you get are that people will, for example, define temperature in 10 different ways. They'll type temperature, they'll type temp, they'll have Celsius, they'll have Fahrenheit, and when you start to try to search for these values, you end up getting sort of a meaningless jumble of different things that comes back. So coming up with a way to really standardize that in a concise manner was harder than we originally thought. So just to give you a feel for what the data looks like, so we have a relatively compact description, but of course it's XML based, so it's not going to be super compact, but the idea is once that the data gets to sort of the internet level, we think that we have enough leeway to actually support a little bit more description of the data. But so here you see sort of an example of a temperature sensor sending a value in degrees Kelvin. So if you look at sort of the physical topology or the physical architecture of the network, you have your sort of sensor layer, which is the transducers at the low end. These could be essentially anything. It's largely out of our control. So clearly we support the FireFly platform pretty well, but we have tens of other different transducer devices that we support. The sort of magic happens when you connect to the gateway layer. So the gateway is what converts that proprietary format into our SOX schema. And so that conversion is done by what we call an adapter. And then that information gets pushed up to our server layer, at which point you're essentially pushing around XML messages over your local network. So from the communication architecture standpoint, we actually use a publish-subscribe based model. So every transducer is essentially represented as what we call an event node. So you imagine having a cloud of these event nodes. Each event node has what effectively looks like an email address to describe its properties and make it addressable within the system. And then you have different sensing devices which publish data to it. Anything that's interested in that data that has access to it can subscribe to that information feed. We also have this notion of meta sensors, where you could imagine having an agent which subscribes to a subset of these devices, do processing on it, and then push that back as a meta sensor. So the sort of simple example there is taking temperature and humidity and calculating dew point. You could, of course, have much more higher level sensing properties, like, for example, occupancy in a room. You could have a different event node which looks at a bunch of sensors in an environment and estimates how many people are there. So the hope is that we could hierarchically compose these things together to sort of pull out richer and richer sensing functionality. Then, as part of the management side, we have what we call a domain data handler. And I think I'd like to just show an example of that in real life. But the idea is that this is the software backend that deals with the registration of devices, searching of devices, sort of sharing of the information feeds. Yeah, so I think at this time, let me switch over from PowerPoint and actually show you. So the first, the easiest way to sort of interface with Sensor Andrew, you can use our development kits, but we also have a web portal, which is where you first go if you want to log in and actually add a device to the system. So here I have a login name, so I'm going to log in with my user credentials. And it turns out that we can actually very easily connect to the Andrew system too, because Andrew also runs an XMPP server to use for our authentication. But when you log in, sort of the first thing you see is this management screen that shows a list of devices which you currently own. So these are devices that I've registered under my user account that I have access control over. And for example, you can click View, and you can see sort of the different properties of the device. So this gives you this meta event node, gives you that essentially ID for the event node. You also see, for example, a QR code that gets generated. So that gives you something that you can put next to the device that links in to the physical instance. So the first thing that we had to sort of solve was this notion of registering a device. So if you have a new device and you want to bring it into the system, you can click on this register link, and then you can either select devices that have already been created by other people. The idea there being able to sort of crowdsource this process of creating and registering devices on the system. Or if it doesn't exist, you can actually say create it, and you'll get essentially a form that pops out on the side that forces the user to go through this process of labeling the sort of important meta information that we need for the system. And so I won't go through the entire process, but once you've created a device, the next thing you need to do is add a set of transducers to it. So for example, you might have an energy meter that reads a panel that has 16 different circuit breakers in it, right? So you want to be able to add different sets of transducers that measure things like active power, or maybe you have something that does active power and airflow. So eventually you can go through and sort of define this device, and it will create this page that shows you your device and then lists these different properties for it. At that point, you can take this information and feed it to the adapters which we've created that will then have the system know how to keep track of the data that's coming in. So the next thing you might want to do is search data. So if you click on the Browse menu, this actually shows us first a map interface. In this case, it's of campus with different sensor nodes. And then below it, you have a list of all of the different sensor devices that are visible at that top layer. So if, for example, I want to search for something like temperature, I can add that filter, and it will actually show me only the relevant sensors that show things like that have temperature sensors on them. I can also, of course, go into a particular building, and then, unlike Google Maps, we also have this elevator view so that you can dive down into subsections of a building. I can click on something like CIC floor level 1 and even go to a particular sensor and see the data feed from the sensor, the different sensors that are available, and click on View History. And here now I'm seeing sort of the last, some snapshot of time of values that the sensor has collected. And then when I zoom in on a particular region, it actually will locally do a higher resolution fetch of that data and pull that out to the user. Because otherwise, if you connect to these sensor feeds, you can get sort of overwhelmed with the data. So we've had to work on developing a backend that can help sort of scale and manage these type of interactions. So just to show some other examples, so if we go to something like Wien Hall, the facility maintenance on campus has been extremely helpful in allowing us to get access to things like building power meters. So if I click on this power meter, this is going to show a device which is monitoring an entire section of Wien Hall. And if you click on here, you can sort of see these power values. The interesting thing to note about this is if you look at, for example, apparent power in Wien, this is in watts. The y-axis is in watts. 400 kilowatts is actually extremely large, right? So your house probably consumes on average, if you have a large house, maybe 3, maybe 6 if you have a really big house that consumes a lot of energy. The type of data that we start to see from our deployments around campus are, orders of magnitude greater than that. So we're hoping that by correlating things like this energy usage with occupancy sensors that we have around buildings, we should be able to infer some sort of really interesting properties about different buildings. Okay. So let me jump back to the end of the talk. So from a scalability perspective, we talked about having to make sure that this system was extensible to sort of internet scales. The idea is that we have server-to-server federation. So you could potentially have one server that's controlling either CMU or a subsection of CMU. We could also have other servers like on the West Coast campus where we can connect to them. And as long as you have a trusted connection between them, then all of our different access control properties can be passed from one domain to the next. The Sensor Andrew portal I already talked about. We also have some other applications. So this is showing you an example of a view that would be available inside somebody's home to essentially show energy usage inside the home rather than just through the Sensor Andrew portal. And we also have a mobile phone version of it. So you can connect to your house remotely through Sensor Andrew, and you can actually look at the different appliances and how much energy they consume. And so here we have some interesting anecdotes that we found. So if you look at, for example, refrigerator, you can actually see that the refrigerator starts to consume more energy when you're cooking because the room tends to heat up and the refrigerator runs harder. You can also see, for example, if you leave the door open, the door gets stuck open, the energy consumption, it'll keep sort of running in the background. You've always got the example like the iron, if you left it on and you want to remotely turn it off. So being able to support that two-way actuation is good. And then this is kind of an interesting example of where anomaly detection really makes sense. So this is showing a plot of my printer at my house, and it turned out that one time it ran out of toner, and so the toner low light turned on flashing. And while the toner low light was on, it actually kept the toner cartridge hot the entire time. So the fact that it was in that state of blinking and not putting the system to sleep meant that it was consuming sort of periodically 600 watts. And luckily, after I had the system in place, I realized that and was able to stop it. But I'm sure there have been times in the past where that light was on just blinking for a couple weeks before I would order the toner cartridge on Amazon. So being able to have visibility into these types of things, I think, is a pretty big deal. So a bunch of other different projects that are being supported by Sensor Andrew. So the Intelligent Workspace now is using it to try to help mediate their problems. We have a couple of projects on pipeline monitoring, environmental monitoring. So we have a sort of a mobile version of this that we're working with the post office to put in people's toilets to monitor the freshness of water, to try to track contaminants in the water supply. Which is kind of an interesting project. So distributing that across the city. And then we also have people who are working on the Green Roof project on campus have information pushing into it. So to conclude, today I talked about multimodal sensing and how we can use that to essentially increase energy coverage. I talked a little bit about this contactless appliance state change detector, that electromagnetic field sensor, which we think has great potential for sort of streamlining this whole non-intrusive load monitoring process. And then I hinted a little bit about some of the next optimizations and plans we have in the future for how we're going to use this energy information and hopefully do further optimizations. So I've got. If you guys have any questions.
cut the energy use? Thank you. When you cut the energy use into 3 big chunks, where do you put like a data center, like Google's data center, in industrial or in buildings?
That's a good point. So I believe right now that's probably an industrial, but it certainly is part of a building, right? So if you look on campus, we have things like the DCO. I think it should be shifted towards buildings because, again, data centers are something that I think we have a great potential for optimization.
So currently, you think they're in industrial?
Currently, I think in that data set that I had, they were probably considered industrial, not buildings. But I guess I'm sure there was some blurring of that.
Okay.
Cool. Well, thank you guys.